That asteroid on Friday the 13th in April in the year 2029 will come close enough to Earth to dip below our orbiting communication satellite. It'll be the biggest, closest thing ever.
Asteroids are a very real threat to Earth, and NASA's recent mission to strike one has everyone talking, and for good reason. In this video, we'll break down how asteroid impacts have shaped our planet, what happens when one comes too close, and the bold steps NASA's taking to protect us. How asteroid impacts have shaped Earth. Asteroid impacts aren't just about destruction, though. They've played a surprisingly big role in Earth's history. Billions of years ago, when the solar system was still forming, collisions were much more common. In fact, one of the biggest impacts in our planet's history might have created the Moon. Scientists believe a Mars-sized object called Theia collided with the young Earth, and the debris from that crash eventually formed our Moon. Kind of wild, right? But that's not all. Water, yes, the stuff that makes up our oceans, might have been delivered to Earth by asteroid impacts. Early Earth was a hot, dry mess, and many scientists think icy comets and water-rich asteroids brought the precious liquid that eventually allowed life to flourish. Of course, not all asteroid impacts have been so helpful. Several mass extinctions over the past hundreds of millions of years may have been caused by big impacts, like the one that ended the dinosaurs. The larger the asteroid, the bigger the impact, and the rarer the event. But just how often do these impacts happen? Let's break it down. How often do asteroids hit Earth? There's an inverse relationship between the size of an asteroid and how often it hits Earth. In other words, small space rocks hit us all the time, while the big ones are thankfully much rarer. Every single day, about 25 million tiny meteors enter Earth's atmosphere. Most are minuscule, ranging from grains of sand to pebbles a few centimeters across. They burn up as they streak through the atmosphere, creating those beautiful shooting stars we love to watch. Throughout Earth's 4.5 billion year history, our planet has been subjected to numerous asteroid impacts, some of which have had profound effects on the course of life. One of the most significant events occurred approximately 65 million years ago, when an asteroid, estimated to be about 10 to 15 kilometers in diameter, struck what is now the Yucatan Peninsula in Mexico. This catastrophic event, known as the Chicxulub impact, is widely believed to have caused the mass extinction of the dinosaurs, along with many other species. The impact released an immense amount of energy, leading to global wildfires, tsunamis, and a nuclear winter effect, drastically altering the planet's climate. Another notable impact event occurred around 4.5 billion years ago, during the Hadean Eon, when a Mars-sized body, often referred to as Theia, collided with the early Earth. This colossal impact is hypothesized to have resulted in the formation of the Moon from the debris ejected into Earth's orbit. The giant impact hypothesis suggests that the collision was a pivotal moment in the development of our planet and its satellite. In more recent history, Earth has experienced smaller but still significant impacts. For instance, the Tunguska event in 1908 involved the explosion of a meteoroid or comet over Siberia, flattening an estimated 2,000 square kilometers of forest. While this event did not result in any known fatalities, it serves as a stark reminder of the potential dangers posed by near-Earth objects. But let's put that into perspective. The biggest meteor likely to hit Earth's atmosphere on any given day is about 40 centimeters across. Not exactly city-destroying material. On a yearly basis, we might see one around 4 meters wide, still not a huge deal. Once a century, though, things get a bit more serious. A space rock at least 20 meters across, think the size of a house, will likely hit. While not catastrophic on a global scale, it could still cause serious damage, especially if it explodes in the air, like the famous Tunguska event in 1908. But not all space rocks just burn up on their way through the atmosphere. So, what happens when meteors survive? Not all space rocks burn up, though. The ones that make it through Earth's atmosphere and hit the surface are called meteorites. These tend to be larger objects that don't disintegrate completely during their fiery descent. By the time they reach the ground, they're usually smaller than what they started out as, often about the size of a brick. These meteorites are treasures for scientists, offering a glimpse into the building blocks of our solar system. If a truly massive asteroid were heading our way, could we stop it? That's where missions like DART come into play. The idea isn't to blow the asteroid to smithereens. That could create a bunch of smaller, still dangerous fragments. Instead, scientists aim to gently nudge it off its collision course with Earth. DART's test mission targeted a small asteroid called Dimorphos, part of a binary system. The spacecraft successfully altered its orbit, proving that we can, in fact, change the trajectory of a space rock. It's a huge step forward in planetary defense. So, with all this talk about asteroid impacts, what's being done to stop them? Technological advancements in asteroid detection and deflection. In recent years, significant strides have been made in the detection and deflection of asteroids, aiming to protect Earth from potential future impacts. One of the most notable advancements is NASA's Double Asteroid Redirection Test mission, which successfully demonstrated the kinetic impact technique to alter an asteroid's trajectory. Launched in November 2021, DART targeted the binary asteroid system Didymos, specifically its moonlet, Dimorphos. On September 26, 2022, DART collided with Dimorphos, successfully changing its orbit around Didymos, marking humanity's first attempt to intentionally alter the motion of a celestial object. NASA. Following the DART mission, the European Space Agency launched the Hera mission in October 2024. Hera aims to conduct detailed investigations of the Didymos system, including precise measurements of the crater left by DART's impact and an in-depth analysis of Dimorphos's internal structure. This mission will provide valuable data to refine our understanding of asteroid composition and behavior, which is crucial for developing effective planetary defense strategies. In addition to these missions, advancements in ground-based telescopes and space observatories have significantly improved our ability to detect and monitor near-Earth objects. Projects like the Pan-STARRS and the upcoming NEO Surveyor mission are designed to identify and characterize asteroids and comets that could pose a threat to Earth. By utilizing infrared imaging, these observatories can detect objects that are otherwise difficult to spot, such as those that do not reflect much visible light. Furthermore, research into alternative deflection methods is ongoing. For example, scientists are exploring the use of nuclear devices to alter an asteroid's course. Simulations and experiments are being conducted to understand the effects of nuclear explosions on asteroid surfaces, including the potential for creating a shockwave that could push the asteroid off its collision course with Earth. While most asteroids stay out of our way, occasionally one gets a little too close. When space rocks get too close for comfort. Asteroids are fascinating and, let's be honest, a little terrifying. Most of the time, these space rocks mind their own business, either burning up harmlessly in our atmosphere or staying millions of miles away. But occasionally, one comes a little too close for comfort. And that's where things get interesting. Let's start with fireballs, because, well, they're awesome. When meteors hit Earth's atmosphere, they often burn up, creating bright trails across the sky. Sometimes, these trails are so big and colorful that they're called fireballs. Picture a streak of light blazing across the night sky in shades of orange, red, or even green. Pretty spectacular, right? Now, most of these meteors are tiny, like the size of a pebble or a grain of sand. They pose no threat, other than maybe giving you a neck cramp from staring at the sky too long. But every once in a while, something bigger comes along. About every 2,000 years, a meteor around 100 meters across hits Earth. That's not big enough to wipe out humanity, but it's definitely large enough to ruin someone's day, especially if it explodes in the atmosphere, creating what's known as an airburst. The shockwave alone can cause serious damage to the surrounding area. Then, there are the true giants. Asteroids over 10 kilometers wide, like the one that wiped out the dinosaurs 66 million years ago. These bad boys come around once every several million years, so the odds of one hitting us anytime soon are incredibly low. In fact, scientists are pretty confident they've already spotted all the big asteroids in our neighborhood and can say with a high degree of certainty that none of them are on a collision course with Earth. But let's not get too comfortable. Even smaller asteroids can pack a punch. Take the Chelyabinsk meteor, for example. In 2013, a meteor about 20 meters wide exploded over Chelyabinsk, Russia. The explosion released as much energy as 30 Hiroshima bombs, and the shockwave damaged 7,200 buildings across 6 cities. Around 1,500 people were injured, mostly from shattered glass. Thankfully, no one was killed. But it was a sobering reminder of what even a relatively small meteor can do. Imagine if that had happened over a densely populated area like New York or Tokyo. It would have been catastrophic. So, what are we doing about this? The first step is spotting these space rocks before they get too close. Scientists have gotten really good at this over the past couple of decades. We've discovered more than 20,000 potentially hazardous asteroids in the last 20 years alone, and we're adding about 30 new ones to the list every week. Most of these have harmless orbits, but the key is knowing about them in advance so we can take action if one ever does pose a threat. So, what happens if we spot an asteroid that could actually hit Earth? Well, that's where things get serious. What if one is heading our way? Let's say, hypothetically, that scientists discover an asteroid on a collision course with Earth. What then? That's where planetary defense comes into play. There have been a lot of ideas about how to deal with this kind of situation. One of the most famous ideas is the nuke it approach, thanks to Hollywood movies like Armageddon. The idea is to blow the asteroid into tiny pieces using a nuclear weapon. Sounds simple, right? The problem is, those fragments would likely still head toward Earth, maintaining much of the asteroid's momentum. So instead of one big rock, you'd have a bunch of smaller ones raining down on us. Not exactly ideal. Another, slightly less flashy idea is the gravity tractor method. This involves sending a spacecraft to fly alongside the asteroid and use its gravitational pull to slowly tug the asteroid off its collision course. It's a gentle, long-term solution, but it requires a lot of advance notice to work. So, with all these ideas floating around, how did we actually start testing out some of these planetary defense methods? The DART mission NASA recently tried a more direct approach with the DART mission. DART wasn't about nukes or fancy gravity tricks, it was about brute force. The mission's goal was simple: crash a spacecraft into an asteroid to see if we could change its trajectory. In 2022, DART targeted a small asteroid called Dimorphos, part of a binary system. The spacecraft smashed into it, and success! The asteroid's orbit was altered. This proved that, yes, we can redirect a threatening asteroid using current technology. DART was a massive collaboration involving NASA, Johns Hopkins Applied Physics Lab, and international partners from Italy, Japan, and the European Space Agency. It's a big deal because it shows we're not entirely helpless against a potential asteroid threat. With enough warning, we might just be able to save the planet. One popular asteroid deflection idea involves blowing it up with a bomb, usually a nuclear one. But as dramatic as this sounds, it's not ideal. Here's why. If you blast an asteroid into pieces, the fragments could still head toward Earth. Instead of one giant bullet, you'd have a deadly shotgun spray of smaller but equally destructive pieces. Not great. Another idea is a bit more sci-fi, using mirrors to reflect sunlight onto the asteroid. If done right, the intense heat could cause outgassing, basically making the asteroid release gases like a mini rocket. This propulsion could nudge it off course. It's clever, but it's also tricky to pull off in practice. You'd need precise aiming and timing, and the asteroid's composition would play a huge role in whether or not it works. So, the team behind DART went with the simplest and most direct option, a kinetic impact. The idea was to slam a spacecraft into the asteroid, giving it a hard shove, not to blow it apart, just to push it enough to alter its orbit. Once they decided on the hit it hard approach, the next step was finding an asteroid to test it on. Finding the perfect test target. This is when Dimorphos steps in, a small moon in a binary asteroid system. Discovered in 2003, Dimorphos orbits a much larger asteroid called Didymos, which was first spotted in 1996. Dimorphos is tiny by asteroid standards, only about 160 meters across, while its big brother, Didymos, measures 780 meters. Dimorphos orbits Didymos every 11.9 hours at a distance of around 1 kilometer. Together, the system orbits the Sun every 2.1 years. The real selling point. In October 2022, the system came within 10.6 million kilometers of Earth, the closest it had been since 2003. This made Dimorphos a prime target for the DART mission. It was close enough to reach without too much trouble, but far enough away that even if something went wrong, Earth wouldn't be at risk. DART was built to be simple, yet effective. Unlike some of the fancy spacecraft you've seen, this one didn't have a ton of bells and whistles. It was about the size of a refrigerator and weighed just 610 kilograms, tiny compared to Dimorphos, which is estimated to weigh 5 billion kilograms. Its main payload was a camera called Draco. This camera was crucial for both navigation and observing the asteroid up close. DART also had an autonomous navigation system to guide it in the final moments before impact. But DART didn't go it alone. It had a sidekick, LYSIA-CUBE, a small secondary spacecraft built by the Italian Space Agency. LYSIA-CUBE's job was to document the whole event, including the crash and its aftermath. Equipped with 2 optical cameras nicknamed Luke and Leah, LYSIA-CUBE separated from DART 15 days before impact, giving it the perfect vantage point to capture the action. So, now that we know what DART was up to, you might be wondering why NASA picked Dimorphos in the first place. Why Dimorphos? You might wonder why NASA picked such a small target for this groundbreaking test. The size was part of the reason. It's easier to see the impact on a smaller object's orbit. Plus, because Dimorphos is in a binary system, scientists could measure changes in its orbit around Didymos with high precision. Any deviation caused by the impact would show up in the orbital timing, making it easier to confirm if the mission succeeded. And let's not forget safety. Dimorphos was chosen because its orbit posed no danger to Earth, even if the mission went sideways. It was a perfect test case, close enough to reach, small enough to move, and safe enough for peace of mind. DART, with its trusty LYSIA-CUBE companion, launched and travelled toward its target. As it neared Dimorphos, DART's autonomous navigation system took over, ensuring it hit its mark. The moment of impact was historic. DART collided with Dimorphos at a staggering speed, successfully altering the asteroid's orbit. LYSIA-CUBE, floating nearby, captured the whole thing, giving scientists valuable data to analyze the impact and its effects. As you can imagine, the distance between Earth and Dimorphos made things a little tricky for DART. It couldn't just rely on us to tell it what to do every step of the way. Flying solo, DART's autonomous tech. Because of the distance between Earth and the asteroid system, sending real-time instructions wasn't an option. The delay in communication meant DART had to figure things out on its own. Enter SmartNav, DART's autonomous optical navigation system. SmartNav was the brain behind the mission. As DART approached the asteroid system, it had to distinguish between Didymos and Dimorphos. It needed to detect the perfect spot to aim for, adjust its trajectory, and line up for the impact, all in the final moments of the mission. Incredibly, all of this happened in the hour leading up to the collision. Within the last 90 minutes, SmartNav locked in DART's final trajectory, ensuring it would hit Dimorphos dead on. DART's journey began on November 23, 2021, when it launched aboard a SpaceX Falcon 9 rocket. Over the next 10 months, it traveled through space, getting closer to its target with each passing day. The real action started about 4 hours before impact, when DART was still 90,000 kilometers away. At this point, its internal navigation system took full control. By the time DART got within 24,000 kilometers, Dimorphos finally became visible on camera, though at first, it was just a tiny blur of 1.4 pixels. As the spacecraft closed in, the images sharpened, and the asteroid system came into focus. Everything was going perfectly. Then, in a final, dramatic moment, DART smashed into Dimorphos at a staggering speed of 6.6 kilometers per second. NASA's goal for the mission was ambitious, to change Dimorphos's orbital period by at least 73 seconds. That would have been enough to prove that a kinetic impact could alter an asteroid's path. But DART exceeded expectations by a long shot. The impact shortened Dimorphos's orbital period by a whopping 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. Even with a margin of error of plus or minus 2 minutes, this was a success 25 times greater than NASA's benchmark. The collision released an incredible amount of energy, 19 gigajoules, equivalent to the explosion of nearly 5 tons of TNT. It blasted a crater on Dimorphos's surface that was up to 150 meters wide, which is pretty impressive for a moon that's only 160 meters across to begin with. After the big moment of impact, you might be wondering what actually happened to Dimorphos. Did it just keep on orbiting as usual, or did it change in some ways? What happened to Dimorphos? The impact didn't just create a massive crater, it also changed Dimorphos in other ways. Before DART's visit, Dimorphos had a nearly circular orbit around Didymos. After the collision, the orbit became more elongated. The force of the impact was enough to alter the asteroid moon's overall path and shape, showing that even a small spacecraft can make a big difference in space. Before the DART impact, Dimorphos completed its orbit around its parent asteroid, Didymos, in 11 hours and 55 minutes. After the collision, this time dropped significantly, eventually settling at 11 hours, 22 minutes and 3 seconds. That's a reduction of over 30 minutes. Even more impressive, the orbital time continued to drift for weeks before stabilizing, showing just how much of an effect DART's punch had. And then there's the shape. Pre-impact, Dimorphos was an oblate spheroid, meaning it resembled a slightly squished ball. Afterward, it became a triaxial ellipsoid, a more elongated form that's often compared to a watermelon. Imagine going from a roundish pebble to a space watermelon. It's a pretty dramatic transformation for something floating in the vacuum of space. Dimorphos isn't a solid, unyielding rock. It's what scientists call fluffy. It's made up of loosely bound material, held together primarily by gravity. When DART collided with it, the force of the impact was enough to scatter and reshape its surface material, giving it a more elongated appearance. This fluffy nature also means asteroids like Dimorphos are surprisingly malleable. With the right impact, they can change shape or orbit quite dramatically. Fortunately, even with these changes, scientists are confident that Dimorphos and Didymos pose no threat to Earth. The collision wasn't strong enough to alter Didymos's orbit in a way that would send it hurtling toward us. DART was a massive step forward in planetary defense. It proved that with enough warning and the right technology, we can protect Earth from potentially dangerous asteroids. While the odds of a catastrophic asteroid collision are low, missions like DART give us the tools to be prepared. So, how exactly did the impact manage to shorten Dimorphos's orbit? It all comes down to the science of orbits. How the orbit shortened. You might be wondering, why did the impact shorten Dimorphos's orbit? It all comes down to orbital mechanics. The crash pushed Dimorphos closer to Didymos, its larger neighbor. Being closer means it now completes its orbit faster, shaving off that extra 32 minutes. To confirm this, scientists used optical telescopes on Earth, like the Southern Astrophysical Research Telescope in Chile. By observing the brightness of the asteroid system, they tracked how Dimorphos moved in and out of Didymos's shadow. This fluctuation, known as the light curve, allowed them to calculate its new orbital speed. Radar data from observatories in California and West Virginia backed up these findings, making it clear just how much the orbit had changed. So, what's next after DART's success? What is Hera, and what will it do? Hera launched on October 7th, 2024, and it's set to arrive at the Didymos system by 2026. Think of Hera as DART's follow-up act, a scientific detective swooping in to study the aftermath of the collision in incredible detail. Equipped with advanced instruments like cameras, a spectrometer, and an altimeter, Hera's primary mission is to map out and analyze the crater left by DART's impact. But that's just the surface-level stuff. What's truly exciting is Hera's ability to dig deeper, figuratively speaking. Using cutting-edge technology, it will probe Dimorphos's internal and subsurface structures. This is a game-changer for understanding not just this asteroid, but the broader mechanics of how kinetic energy impacts near-Earth objects. By studying the asteroid's composition and the way energy is transferred during the impact, Hera will help scientists refine their models for asteroid deflection. We'll gain insight into how momentum transfers to both an asteroid and the material it ejects during a collision. All of this will make future deflection missions more precise and effective. Hera's work will go hand in hand with NASA's growing efforts to track and study asteroids. One major upcoming project is NEO Surveyor, a space telescope scheduled to launch in 2028. While NASA already monitors the vast majority of known NEOs, the focus is now on spotting the trickier ones, objects like dark comets that don't reflect much visible light, making them harder to detect. NEO Surveyor will use infrared imaging to track these stealthy asteroids. Unlike visible light, which reflects off an asteroid's surface, infrared detects the heat emitted by objects as they're warmed by the sun. This allows astronomers to pinpoint even the hardest-to-spot NEOs. The telescope will also tackle one of Earth's biggest cosmic blind spots, asteroids approaching from the direction of the sun. Ground-based telescopes often miss these due to the sun's glare, but NEO Surveyor's infrared technology will be able to spot them easily. The combination of Hera's deep dive analysis and NEO Surveyor's wide-ranging detection capabilities is like building a two-layer cosmic shield for Earth. For the first time, humanity is actively reducing the likelihood of being blindsided by a world-ending asteroid strike. Think about it. The same kind of impact that wiped out the dinosaurs no longer feels inevitable. If a hazardous asteroid is detected early enough, we now have the tools and growing expertise to nudge it off course and save our planet. And while the chances of a major asteroid collision are slim, the consequences would be catastrophic. That's why missions like DART, Hera, and NEO Surveyor are so crucial. They're not just about protecting Earth, they're about giving humanity a fighting chance against one of the few natural disasters we can actually prevent. Now, shifting from planetary defense to a spot right here on Earth. The Wolf Creek Crater. Wolf Creek Crater, located in the remote Kimberley region of Western Australia, is a place that feels like stepping into another world. Imagine standing on the edge of a massive, ancient crater, gazing out over a vast expanse of red desert and rugged terrain. It's a spot that makes you pause and think about the forces of nature that have shaped our planet. This crater isn't just any hole in the ground, it's the second largest meteorite impact crater on Earth. Measuring about 880 meters across and 60 meters deep, it was formed when a meteorite, roughly 15 meters in diameter, slammed into the Earth around 120,000 years ago. The impact released energy equivalent to 36 times that of the Hiroshima atomic bomb, creating a crater that has stood the test of time. Getting to Wolf Creek Crater is an adventure in itself. The journey takes you through the heart of the Kimberley region, a place known for its rugged beauty and isolation. The nearest town, Halls Creek, is about 145 kilometers away, and from there, it's a 50-kilometer drive on a well-maintained gravel road to the crater. Along the way, you'll pass through the Great Sandy Desert, a landscape that feels both desolate and beautiful. The road can be challenging, especially during the wet season, so it's important to check local conditions before setting out. Once you arrive, the first thing that strikes you is the sheer size of the crater. Standing on the rim, you can look down into the bowl-shaped depression and imagine the cataclysmic event that created it. The surrounding area is dotted with spinifex grass and scattered trees, and the sky above is often a brilliant blue, making it a photographer's paradise. The contrast between the red earth and the blue sky is something you'll remember long after you leave. For those who enjoy a bit of exploration, there are walking tracks around the rim that offer different perspectives of the crater. The 200-meter return walk to the top of the crater rim involves a steep, rocky climb, but the views are well worth the effort. It's a chance to get up close to the geological features of the crater and appreciate the forces that shaped it. However, climbing down into the crater is not permitted due to the steep terrain and loose rocks, which can be dangerous. The area around the crater is rich in wildlife. You might spot kangaroos hopping in the distance or see a variety of bird species soaring overhead. The region is also home to unique plant life adapted to the harsh desert environment. It's a reminder of the resilience of nature and the delicate balance of life in such an arid landscape. Wolf Creek Crater holds significant cultural importance for the Jaru First Nations people, who call it Candimalal. According to their legend, a rainbow snake emerged from the crater and formed a nearby creek as it slithered away. What do you think? Leave your thoughts in the comments below. And if you liked this video, don't forget to subscribe to our channel. See you in the next one.